Hey there, physics folks. In this video, we're going to take a look at the second part of the practice problem for non-conservative forces and energy conversions. So in the first part, we had a roller coaster that had no friction and no air resistance, and it was moving at 6 meters per second. It was going to drop 127 meters, and we needed to find the speed at the bottom. Now, because there was no friction, it was just a straight up energy transfer. So we had the potential at the top because of the height. The slow speed of 6 meters per second gave us some kinetic energy. We went down to a zero height here, so we had no potential energy at the end. So all of the energy at the beginning turned into all kinetic energy at the end, and we ended up with a speed of 50 meters per second. What this second part says is, hey, in reality, there are non-conservative forces such as friction in play. They do actually act on the roller coaster when it goes down. And that means that as the friction drags this thing down, we're going to end up with a slower speed, because as we know, friction is going to cause that speed to slow down. It's going to be less at the bottom. Now, in terms of energy, what that friction does, it actually does work. And the work done by the friction is equal to the change in energy of the system. Now, why would energy change? Well, energy can change forms, but what we're talking about here with the work is equal to the change in energy, it means that the total energy available here of this roller coaster and the total energy down here of this roller coaster are different when there's friction involved. So in the first part, the total and the total were the same, but when there's friction involved, we're going to take some energy away, and so we're going to have a change of energy. And that's why the speed down here when there's friction is 45 instead of 50, because of course it's going to be going slower because friction is going to slow the roller coaster down from what it normally would have been. Now, again, another way of saying work is the change of energy is we can say that W equals delta E. And we know anytime we do delta something or change in something, it's always final minus initial. Now, it's pretty easy to see that if the final energy and the initial energy are the same, as in the case when there's no friction and no air resistance, if the final energy over here and the initial energy over here are the same, if final minus initial, if this is the same, then we're going to have zero work. So in other words, if this is, 100 joules and this is 100 joules, 100 minus 100 is 0. However, because this friction takes away some of the energy and we have less energy available, mechanical energy of the car down here, that means the final energy is going to be what we might call as lesser. And the initial energy is greater. And that's because we've lost some energy on the way down. Now, it's pretty easy to see that if you take a small number or a lesser number and you subtract a greater number or a bigger number, this work is going to be negative. Now, work isn't always negative, but non-conservative work and non-conservative work done by non-conservative forces like friction is always going to be negative. It's always going to pull energy away from the equation. So I'm going to do this problem in two ways, because the first way gives you an idea in terms of taking a lesser energy and a greater energy and finding the negative work. And then we'll take a look at it in a more conceptual way. Okay, so the first way is we're going to do it just like it says here. So the work is equal to the final energy minus the initial energy. Okay? Now, another way of saying this is also saying, we could say that the work is equal to the change in energy, as we said. But remember, change in energy means the change in both energies. So I'm going to say work is equal to the change in potential energy plus the change in kinetic energy, because of course the total energy is simply potential plus kinetic. Now let's see if we can write this out and see if we can come up with an expression that makes sense. Okay, so I'm going to change colors a little bit. I don't know if you can see that on the screen. It's slightly different. That's a blue. What's potential energy? Well, it's final minus initial. So that's going to be mgh final, which remember is down at the bottom, minus mgh initial, that's up at the top. Now notice that's a small number, in fact it's 0, and this is a bigger number, so we're going to get a negative number. So that's the change in potential energy, and that's going to be plus the change in kinetic energy, which of course is 1/2 mv final squared minus 1/2 mv initial squared, because of course that's the change in energy final minus initial. And I think you can probably see that the final is going to be a bigger energy because it's going 45 meters per second, and the initial is going to be lesser, and that's going to, so this is going to be a positive number, this is going to be a negative number. Okay? Now I'm going to factor, let's just factor some things really quickly. So, well, actually, before we factor anything, let's factor it now, and let's see what we can see here. Okay, so we say W equals mg h final minus h initial. Am I still on the screen? I am. Plus 1/2 m, that comes out of both of those, v final squared minus v initial squared. Don't forget to keep the squares with the velocities. Okay? And so again, now I'm going to try and keep that roller coaster. Well, it might go off the screen, but you guys know what's going on here. I'll draw it very quickly. We're going from here to here, and this is 127 meters. And this is 6 meters per second. This is 45 meters per second, just so we can keep that in line. Okay? And remember, again, we're losing energy because of friction here, and that's a pretty straight vertical drop. All right. Well, let's just go ahead and plug in some numbers and see what we get. Okay? Now, it's easiest to see if we go W equals, what do we got? Well, we got 55 kilograms times 9.8 meters per second squared times what's in this parentheses. Well, H final is 0, H naught is 127, right? So that means this is going to be negative 127 meters. All of that, and let's just put that in brackets because change in potential, that's the change in potential, so that's what's in that bracket. And we're going to add that to the next bracket, which is going to be 1/2 55 kilograms times parentheses 45 meters per second squared, because that's what it's doing at the bottom. That's the velocity it's contributing to the final kinetic energy, minus the initial 6 meters per second squared, and that's contributing to the initial kinetic energy. Okay, and then we're going to put that in brackets. So these black brackets here represent the changes in potential here and kinetic here, total. We went ahead and said this was 0, so this is just negative 27. Now, if you do some math, I don't normally do this. I don't normally write the intermediate steps, but if you do this first bracket here, this ends up being negative 68453 joules. Okay, and check it out, it's joules because it's kilogram meters per second squared. That's a Newton times a meter. That's a Newton meter. That's a joule. And this one comes out to, check your math, check your calculator, 54,697.5 joules. And I think you can pretty clearly say, we'll put a plus sign in there and put the equal sign in here and put W over here. I think you can pretty clearly see that the change in potential energy and the change in kinetic energy are different. So we're going to have a non-zero work here. More importantly, we're going to have a negative work here. And the reason we're going to have a negative work is because the change in potential energy is bigger than the change in kinetic energy. If they were the same, we would have 0. Now, why is the potential energy bigger than the kinetic energy down at the bottom? Well, we lose all the potential energy, but we don't gain the same amount of kinetic energy because some of that is lost to work done by friction. Now, work is not energy. Work is the change in energy, or has the function of changing energy. So it's basically the idea that we have a total amount of money up here in our bank account. We have some money left. We have some money left over here, down here, but we've lost some along the way. Maybe we've made some investments, right? We've changed some investments from our potential savings to, a more active investment of money down here, but we've lost some money along the way due to costs of investment, if you want to think about it as an economics thing. The idea is you got the whole loss of potential, but only some of it goes into kinetic. And if you do the addition, it's no big deal. You end up with work equals negative 13,755.5 joules, which checks out to 1.4 times 10 to the fourth negative. Okay? Now, again, work non-conservative is almost always going to be negative. Now, very quickly, I'm going to do the same thing, but I'm going to take a look at it from an energy bucket sort of standpoint, okay? And what I mean by that is I'm going to, let me move this over here and see if we can get this all the way over here, and I'm going to take a look at it from a little bit different standpoint, okay? Now, I like to think of energy as an amount of stuff. Okay, and we know that there's a certain amount of energy up here, and that's what we said. There's energy initial at the top, and there's energy final at the bottom. Okay, so the total energy at the top at the beginning is PE initial plus KE initial. Now you can do this either way, but I want to just show you this in terms of sort of what I call the bucket approach. And when I say the bucket approach, I mean we've got a bucket full of energy here, and we've got a bucket full of energy here. Now when it gets to the bottom, we're going to move into potential energy at the bottom, final, pardon me, plus kinetic energy final. Now that would be fine, and that's in fact what we did up here when we looked at the conservation of energy, and it just all went into kinetic energy here. Okay. However, what we want to think about now is, now that we have this non-conservative force, we know there's going to be something else. Okay. So again, beforehand we've got this much energy, and afterwards we're going to have this much energy if there's no friction. However, we know that because we've lost some energy due to friction, we have to take some of this energy and pour it into another bucket, and that's the lost energy. And so I'm going to say that lost energy we can call the non-conservative work. Okay, the work non-conservative, which is what all these works are anyway, right? This is all non-conservative, non-conservative, and non-conservative, and non-conservative. Why do we call it non-conservative? Because it doesn't jive with the conservation of energy. Now, what does this mean? Well, let's just do a little elimination here. We know the potential energy is at the bottom is going to be 0. So now look at what we've got. We've got our same mgh initial at the top plus 1/2 mv initial at the top equals ke final 1/2 mv final squared. Now that's what we had in that first problem when we had no friction, and this is when we came up with 50 meters per second here. However, some of that energy has to go into doing work. Now why is it a plus here? Okay, why is it a plus here? Because the total buckets of energy here, we've got 2 buckets. We've got a potential bucket and we've got a kinetic bucket. And the amount of energy in those 2 buckets, in the original problem when there was no friction, it all got dumped into the kinetic bucket. Okay? And so all of this energy got dumped into one bucket. In the second part, where there is friction, we now not only dump some into the kinetic energy, but we run out because some of it gets taken away and goes into the non-conservative work. So we got joules equals joules plus joules. Okay? Now another way to look at it in the terms of this bucket idea is that if we start out with mgh naught plus 1/2 mv naught squared, we know that this speed over here is less. Well, why is it less? Well, look, if this bucket is being filled over here, that was energy that was taken away from this total over here. So if we just algebraically take this over to the other side of the equal sign. That's minus Wnc, and that's going to equal 1/2 mv final squared. So if you look at it this way, you got the total energy at the beginning, subtract out the work done by friction. So this number of joules over here, subtract this number of joules over here, and you end up with this number of joules over here. Okay? So if you want to think about it as the energy, the work is equaling the change in energy, and just looking at final minus initial and seeing that this is negative and this is positive, because of course potential energy decreases, kinetic energy increases, but there's some loss, and that's the non-conservative work. Or you can think of it as the bucket approach. You know, you've got a bucket of energy here, a bucket of energy here. You're going to pour some into here, but some of it's going to be taken away here. Or you can think of a whole bucket of energy here, take away this many joules away from that bucket of energy. It gets spilled, it gets lost, it gets dribbled onto the floor, and what do we have left over in our final bucket is just the kinetic energy. But I think you can see that this speed is going to be less than if it have work. So in other words, you can see now conservation of energy, total mechanical energy equals total mechanical energy. However, if we add that friction in, we're going to lose some of that energy, so we're going to have a lesser amount of kinetic at the end. Hopefully that was clear. If that was a little too belabored, feel free to rewatch it in double speed if you want, but hopefully you'll have a little bit better understanding for non-conservative work. All right, see you guys next time.